Good morning and good afternoon to our speaker. And thank you for joining us for the 28th webinar in the Offshore Wind series, Learning from the Experts. I'm Kate McClellan-Press, Senior Project Manager on NYSERDA's Environmental Research Team. And it's my pleasure to be joined by today's expert, Henrik Skov with DHI. Before I introduce our speaker, a few reminders for participants and some background on this webinar series. Next slide, please. Firstly, if you are experiencing any technical issues, please contact Sal Graven at the email address at the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in this series will be available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speaker. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goal of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select Learning from the Expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for a future webinar, you can email us at offshorewind@nyserda.ny.gov or fill out a survey also available on our website, nyserda.ny.gov /OSW-webinar-series. Please note that the views and opinions expressed in this presentation are those of the presenter. Next slide, please. It is now my pleasure to introduce Henrik Skov. Henry is a senior project manager in offshore wind at DHI. He has more than 35 years of expertise in the application of field and analytical methods for assessing marine habitats and the related effects of human activities at sea. He has gained experience from over 50 marine strategy and impact assessment projects and has also held the position of technical lead and project manager for many offshore wind, agent-based modeling, habitat modeling, and impact assessment projects. Henry has been instrumental in developing automated monitoring approaches for birds in relation to offshore wind projects and the application of dynamic habitat modeling, GIS-based decision support systems, IRT assessment of wetland importance, and sensitivity mapping. His experience record includes small and large-scale marine protected areas, oil and gas, sustainable commercial and artisanal fisheries, sustainable offshore wind farms, and dredging activities. Thank you, and I will now hand things over to Henrik.
Thanks a lot, Kate. Yeah, it's a real pleasure to have the opportunity to share some experiences and also ideas about how to use movement models in relation to offshore wind development. This has been the movement models or spatial models of distribution and movement of seabirds and marine mammals have been very useful in Europe, and now we are seeing the same urge in the US. I'm happy to have been involved in a project for NYSERDA together with VSP and Advision, and I will share mainly some data from this project, this new project, data in progress, I would say, or models in progress, but also some data from projects I've been involved with in Europe. So I think the overarching idea here is that we really need very detailed and at the same time data that cover very large areas about the distribution and movements of birds and mammals in these areas that are now being targeted for offshore wind. We need to be sure that we actually site the projects correctly. We need them to be sure that we can actually assess the impacts before providing the license to these projects. And we also need them in order to interpret monitoring results during and after construction. It's a huge undertaking because most of the data that are available from surveys in the past, most of the data that will be collected in relation to each of those projects, they will for sure be fragmented both in time and in space. So to get a coherent view of the distribution, and at the same time a data that can show us the kind of detail we need in order to assess what goes on in relatively well-defined smaller areas, that's a tall order. But that's actually what the spatial models can help us to do. Spatial models have been existing on land mainly for years, have also been applied offshore, but they have mainly been used in a way that is very difficult to apply in or to just copy when you want to understand in detail the distribution and movement of animals. I think the term that is often used here is ecosystem-based management. And I believe that that is exactly what is needed in relation to offshore wind, and why the best available data on the distribution of birds and mammals is absolutely necessary. Data from single surveys will not be sufficient. It will be necessary to show the perspective of this distribution in relation to what is specific in the ocean, what are the particular characteristics of the marine environment that is important in relation to these different species. It's actually a lot of the activities around offshore wind where we need these very detailed maps that cover large areas. We need it for very early marine spatial planning, where we look at where we can actually site offshore wind farms without conflicting with other uses of the marine environment. We need these data certainly for strategic assessments once we have all the different potential sites on a map. Then we need them for impact assessment. We need them to understand the cumulative impact assessment of all the different projects being developed. And we need them following construction. We need to understand or interpret monitoring results in relation to sort of the wider distribution, understanding the whole perspective of what we have found. And so there's a lot of different, it's actually the whole process of offshore wind development that needs this information. And that is why it's great to see the NYSERDA have actually started this project. It's a good starting point, I think. The big challenge when you start working with spatial modeling offshore is that all the data, all the sort of standard models we are working with, they have been developed based on land, and they have been based on landscape ecology and data about habitats that do not change very often. They of course change with seasons, but they don't change in the same way as habitats in the marine environment. Once we go into the marine environment, what we see is that most of the models that are developed, they use what I would call semi-static habitat information, like well, bathymetry or seasonal averages of temperature or currents even, but they don't actually describe what goes on exactly at the time when an animal is observed. And this creates a lot of uncertainty. What happens when you average distributions over time, I think it can be illustrated by this graph. It shows which processes in the sea tends to concentrate predators most. It's all the different processes that we look at, the different oceanographic habitats. They are plotted here in relation to time and spatial scale. And there's a very distinct cluster of those processes that are the most influential. And they are more or less at a scale that is smaller than 10 kilometers. So what happens when you average patterns over time, for example, by correlating observations to seasonal mean temperatures, is that you will underestimate densities exactly where the animals are concentrated, and you will overestimate densities in the periphery of where the animals are concentrated. So over large areas, you will actually overestimate densities. So that's the problem of using mean values to drive the models. This graph here also shows how much variation you have. The variation we see here is oceanographic variation in an area in the North Sea. We look at salinity, and it's actually the tidal oscillations. So changes from over like every 3 hours you have a change in salinity, and quite some change actually. So by averaging over time, you're not able to relate an observation with the oceanographic conditions exactly at that spot at that time. It can also be illustrated, I think, by this video. Shows a modeled salinity in an area of the North Sea. It's a plume from a river that actually influences bird distribution and movement a lot. And over these 10 days, you can see that this frontal area, which concentrates prey and the red-throated loons, it moves quite a lot from actually just from hour to hour. So when we develop these spatial models offshore, we really need to link our observations with the conditions exactly at that time, at that place. So I will go through the different steps of dynamic or movement modeling. It involves 3 different types of modeling. One is the flow modeling concept, hydrodynamic modeling, which is essential to get the correct drivers for the more ecological models, the dynamic habitat modeling, and the agent-based modeling. The dynamic habitat models, they predict where the animals are mainly distributed. While the agent-based models, they actually use that information together with other kinds of information, knowledge about the behavior of the animals, movements of the animals. They predict both the distribution and the movements, for example, seasonal migrations, foraging movements, etc. So once you get to the level of the agent-based modeling, you should get as close to reality as you can with the knowledge we have. This overview of the different tasks involved is from NYSERDA. So there's a very important first step in quality assuring data, collecting data. All this modeling activity is very hungry when it comes to good quality data, and of course also post-processing those data into what is useful for modeling. Hydrodynamic modeling is the starting point, and then looking at how, trying to understand how our data covers the different habitats that can be extracted from the hydrodynamic modeling. Once we know the quality of the data, we can then start the modeling processes. This is an example from Europe, actually. It's a project for Ørsted I did some years back. That shows how you can downscale if you have the calibration data available. This is from a mesoscale model showing a part of the Northeast Atlantic, down to a local model which shows the southern North Sea and the Channel, and then finally ending up with a fine scale model which has a very high resolution, so 1 grid point at each of the turbines in this planned wind farm. So that is the perfect way of doing it post-construction. Of course, in the NYSERDA project, there are no wind farms yet. And this is the way that our model grid was looking like. So we had a high resolution in the areas with low water depth, and then gradually coarser resolution with depths. When we look at the data, this is often a very big task to quality assure the data, to calibrate the models. Often it takes a lot of the effort needed to set up the models, and that was also the case here. So it's here for the hydrodynamic model. We of course needed bathymetry. We needed data on meteorology, on currents and waves from buoys. We needed also discharge data from the rivers and model the wind and wind direction and speed. For dynamic habitat modeling, it's actually survey data that is needed, and we did have access to a lot of high quality data from different types of platforms. For the agent-based modeling, it's more knowledge that is actually needed. It's literature, but we also had telemetry data available that gave us, for example, exact timing of seasonal migration movements. The data quality, as I mentioned before, it actually takes the output from the hydrodynamic model, and then it analyzes it in terms of different oceanographic provinces. The graph here to the left shows the different types of habitats defined by salinity. So you could say that the area here along the coast is a lot influenced by fresh water, and then you have the oceanic area with high salinity here in the deep water, and then a mixing sort of water mass in between. This one here shows current speed. So we have high current speed in the deep water. You have low current speed along the coast, and then you have again an intermediate situation in between. So again, longshore patterns of these oceanographic provinces. And the one here to the right shows the one here to the right shows the different levels of stratification. Stratification is extremely important for predicting the distribution of predators, and we see that the area along the coast is mixed, while the area further offshore is stratified most of the time. If we move to the concept behind dynamic habitat modeling, it's actually about taking the data, the observations in geographic space, and then reprojecting that with the oceanographic data from the hydrodynamic model into what you could call an oceanographic space. And then reprojecting back into geographic space by using a statistical model, correlations between the observations and then the oceanographic conditions exactly at the location of those observations makes it possible to generalize patterns by taking the output again from the hydrodynamic model and then applying those models for different scenarios. It could be exactly at the resolution of the hydrodynamic model. That would be 1 hour. So you would actually have a prediction of a distribution every hour for as many years as you have developed this hydrodynamic model. But you could also want to actually predict on an average over longer time periods. Normally, and that was also the case here in the NYSERDA area, the prediction models are split into presence absence and then positive density. The positive density is then only predicted for those grid points where you have presence. The assessment of the quality of the models is done both for the explanatory power and in terms of the predictive power. So that those are standard ways of validating the models. There are many different ways of doing that. I'll not go into detail with that. A lot of the predictors we are using, they are taken directly from the hydrodynamic model. So it's stratification indices, it's frontal indices of different kinds, it is information. So these are indices that are developed from the raw data on currents and also temperature, salinity gradients. This is an example of how a visualization of the result would look like if you look over a 10-day period. So it's hour by hour, the distribution of northern gannets. This is a species that's very much linked to the coastal environment. It likes to be in the mixed water mass, but it also is common, especially in the Hudson River Valley, and sometimes they venture offshore. But in general, they're very coastal. But you can see the dynamics from hour to hour. This is fin whale. This is much more a wide distribution. They are actually in this area all the time, it seems. They're not inside in the Long Island Strait, but otherwise they are everywhere, even in the deep water. But there is a tendency for the highest densities along the shelf edge in the interface between stratified and mixed water mass, and also in the Hudson River Valley again. These types of models, where you try to link observations to dynamics in the environment exactly at the right time and place, they can also be used to predict how birds are flying. And of course, the flights of birds is one of those elements that are important in relation to wind. The collision risk is high on the agenda. So if it's possible for you to understand or use observations, tracking data, for example, of birds to generalize movements, how high do they fly in different situations, how are they distributed offshore in this region, then you have a very good planning tool. And we have also been using that for projects here in Europe. Here's an example for a strategic study we did in the Baltic Sea, looking at how high crane, it's a bird called a common crane, it's a very large bird, like a 2 meter high, and with a high conservation status. So this was very much in focus when developing wind farms between Germany, Sweden, and Denmark. So here's an example of trying to predict how high do these relatively rare birds, how high do they fly in different weather conditions. This day here is a day with relatively strong winds. They are flying a lot at rotor height. The following day, we are predicting for a day with more optimal wind conditions, and then the birds are predicted to fly mainly above the height of the turbine. So information like this can really feed into assessment of collision risk and trying to get a stronger basis for concluding what will be the overall effect on these birds if you look over many years of weather conditions. The next level is agent-based modeling. So this is actually going from population modeling to individual animals. In order to do that, you try to simulate the movements of individuals or groups of individuals from the knowledge we have about seasonal migrations, for feeding behavior, social behavior, etc. This is quite complex. I will not go into much detail. I will show the design of the red-throated loon ABM. So it's actually composed of a decision tree where different elements play a role, and you have, as a scientist, as a modeler, you actually have to define it yourself from the knowledge that is available. So it's not like for the hydronym for the habitat models, where you actually let the computer more or less do the job for you. Here you have to code the relationship. You have to code the decisions from the knowledge you have. The internal state is the first point, and most important is the energetic level of the animal, the migration, whether it's on migration or not. Does it need to forage? What is the general pattern? That's very important for the red-throated loons. And then you then move into a decision concerning habitat. is a habitat of sufficient quality, or does it have to move to the next habitat or area? The wind conditions, are they optimal, or will it actually have to drift with the wind before making the final decision on whether to fly, swim, dive, or rest? So this is done for all the individuals in every time step in the model, so every hour, and then you can summarize this information and show how the general movement of the animals or the birds are in this period. The same is true for the fin whale. Here it seems like they are actually residing in the New York Bight all the time. So it's not like we have no information about seasonal migration, but otherwise it's a similar design of the ABM. It's important to validate at what scale these models are actually useful. This is a way to validate that by looking at the correlation between the model density and the observed density at different scales of data from 10 to 100 kilometers. So you can see that the model predictions fit the observed densities better at larger scale. So for the fin whale, it's clearly a large scale model. So more data would be useful. For the other species, like the red-throated loon, the predictions at finer scale are better. So let's have a look at the applications in relation to offshore wind of these technologies. As I mentioned before, you can use these models almost during all the phases of offshore wind development. When you decide on the suitability of the site, it's interesting to use them to understand where you have migration corridors, where do you have hotspots of animals and birds. Maybe you want to avoid those when you are siting project areas. For baseline surveys in relation to impact assessments, those models can be very useful in order to provide the data for estimating habitat displacement, collision risk, etc. Construction monitoring is not so common, but I still believe that it can provide, these models can provide important information in relation to construction monitoring in order to understand avoidance of the wind farm, of individual turbines, how the behavior of animals and birds changes during construction. But certainly in the post-construction situation, it's one of the only ways that you can actually control for the natural variability. There's a lot more variability in a wind farm when it comes to animals, their distribution and movement, than is actually related to the wind farm. So, but I will come back to that. In strategic phase, I think that's where we are with the NYSERDA project I've been involved with. So one way to generalize all those model results is to show the mean seasonal distribution of the animals. And this is Loggerhead turtle. They are very much related to the what you could call the shelf fronts, so fronts between stratified and mixed water masses, and they clearly avoid the deep water or even the shelf edge. If we move to northern Ghana, they are even more coastal, so they are more or less completely within the mixed water mass to some extent. They are also over the shelf, but they are mainly in the mixed water mass close to shore and up on George's bank. Red-throated loons, different story. They are mainly where you have the river plume front between the big estuaries, the Hudson River, and the shelf water. That's where you have the highest densities. And then you see a tendency for in winter time, they actually concentrate in the southern part of the area. You can use the ABM, for example, for the red-throated loon to illustrate seasonal migration towards these bays, the Pimlico and Chesapeake Bay, those areas and the offshore areas of those bays, which are very important. You can see those. The movement is very almost linear. It doesn't take long for the birds after they arrive from the Arctic to settle in in those core areas. For the fin whale, it's very different. We see that they are more or less dispersed all over the shelf, or with a tendency for higher densities along the shelf edge in the Hudson River Valley, and perhaps also like a band of higher densities when you reach the front between mixed and stratified water masses. If you look at movements, because they seem to reside in the area for long periods of time, it's actually the movements look like local movements with a scale of maximum 100 kilometers. So no seasonal migration as we see it. But you can of course use this data to extract much more statistics. These are just visualizations. If we move to impact assessment, I think one of the main uses of these models is to apply the flight models in collision risk assessments. So this is an assessment I've been involved with where we use wind to predict how high birds of prey are flying in an offshore wind farm before it is built, and then we can actually predict clearly that they fly above the rotor in tailwinds, and in headwind situations they actually fly at rotor height. So the collision risk is mainly related to headwinds. So information like this is very useful in impact assessments. If we move to post-construction, what we are looking at post-construction is in a wind farm. This is a wind farm in the Netherlands, by the way, where there have been data collected since 2002. These are the number of northern gannets that have been seen on each survey within the wind farm, or the density actually. What you see clearly is an enormous variation in the number of birds, which is way beyond what can be related to the effect of the wind farm. So what we are looking at here is a lot of natural variation that affects the number of birds in the wind farm. So how do we actually assess the impact when we're doing monitoring of birds and mammals in these wind farms? And I think that's a key question. And so far, I don't think that the monitoring programs have actually shown actual impacts and have shown differences between baseline and post-construction, but that is not necessarily the actual wind farm related impact. We did some work on that for wind farms in the Netherlands, where we took account of the oceanographic variability, and we could see that that actually helped a lot. Here we have a situation where pre-construction there are less of these birds and northern gannets in the whole area than you find after the wind farms are built. Even inside the wind farm, you see more birds than before the wind farms were built. But if once you actually take account of those changes, you can see that the increase in density in general in this part of the North Sea is much higher than what you have seen in the wind farm. So it is possible to identify a habitat displacement, even if there is an overall increase in the number of birds. So I think this is a good way to use these models to improve the power of post-construction monitoring. I don't think it has been sort of demonstrated to a large extent. So here there's an obvious aim for in the future, both in Europe and in the US, I think. Thank you.
Thank you so much. And we have plenty of time for questions. And I just want to remind attendees that if you do have a question, please use the Q&A function at the bottom of the WebEx screen to submit them. And I think we'll get it kicked off with one question related to, you talked about how these models are data hungry. And how does that influence which species you've chosen for dynamic and agent-based models, maybe using the examples from the New York Bight or other projects that you have worked on?
Yeah, it's actually the amount of data that determine which species you are able to work with. So even in the NYSERDA area where there were lots of data, we were challenged. For the birds, we had plenty of data. For the northern gannets, we have lots and lots of survey data. For the red-throated loons, we even had telemetry data, so satellite tracking data. So that helped a lot. For the turtles and for the fin whales, it's more difficult to get a lot of survey data. So I think it is still a compromise for those species, and we would have been able to improve the models with more data, no doubt. For the birds, I think we had what we needed to predict the distribution.
Thanks. And a similar question on oceanographic data. I think you described some of the data sources, and the question was around, you mentioned that most of the sources can only give you daily or monthly averages, and yet you're able to kind of project on a much more fine scale level. Was that the case, or did some of the oceanographic data have more fine scale resolution than that?
Maybe I did. Maybe that was not clear. Sorry for that. But we actually developed a dedicated hydrodynamic model for the NYSERDA area. So we did have fine scale flow data available.
And can you maybe talk about kind of how, what is necessary or what kind of data is necessary for getting that fine scale information for these models?
Yeah, you need to calibrate the model with input data on currents, especially the information about how our current speeds, etc. With depth. You need that for several locations within your model area for long periods of time. So you need to calibrate to set up a model also with input on, for example, discharges from rivers. You need to have very good information on weather conditions, winds, of course. And once you know that the model is well calibrated, then you can actually produce hourly predictions back in time for as long as you have those calibration data available. So in the NYSERDA area, I think we went back to 2018. And in some projects I've been involved with, we have sort of trying to reconstruct the history back like 10 years back in time. So that is possible if the calibration data are available.
Thank you. Kind of switching topics a little bit, but can you talk about how movement models like these have been used by, I think, regulators in Europe around offshore wind development, or I guess even other industries that you've worked in, and how it might help focus site selection or other kind of strategic planning purposes?
Yeah, it's been I've been involved in it, especially in Denmark, in strategic studies where we have used these models and where we have been able to see that the Ministry of Environment have actually used the output from these models to select the areas that they want to pursue for wind farm development. So I think Denmark is probably the only country where these models have been used that aggressively, I would say. In Denmark, there are some ambitious plans to develop wind energy islands, both in the North Sea and in the Baltic Sea. And after we developed these models, those areas were defined to a large extent based on where we could see there would be issues if wind farms were developed in those specific areas. So I think in Denmark at least it has been carried out. I'm not aware of any other strategic studies that have used these models in that way. Not really, no, unfortunately.
Well, you've also talked about how the movement models can be used to assess monitoring requirements further down in the offshore wind phases, like post-construction. Can you talked a little bit about some of the ways it has been used for birds. Can you talk a little bit more about how we might learn from these models and design post-construction monitoring efforts, especially around I think you're getting at that, the need for having specific questions to detect impact.
Yeah, I think these are key questions for any sort of regulator. What should be the monitoring requirements? What is actually needed to get the power to show a certain impact? And then your knowledge about the natural variability is going to be key. Otherwise, you are making false assumptions, and your monitoring requirements will be falsified. And that's what I think we are seeing in many places right now, that people are assuming that this environment is stable, that the abundance of birds is the same for long periods of time. But you could see from the example I showed from the Netherlands how much variation you have from survey to survey, just because of the changes in habitat. You can imagine water masses moving in and out from a wind farm. So how to deal with that when you have to come up with or identify monitoring requirements? I think the best way to do it statistically is, first of all, to try to predict the distribution of the birds without the wind farm. So reconstruct the natural variability without the wind farm, and then simulate the effect of the wind farm from what is known about from observations, how far away will animals be affected by this wind farm. And then you, based on those simulations, you can then you can actually rerun these models with the simulated data set, and then you can get an estimate of the relative influence of the wind farm compared to all this natural variability. And then you're in a good position to try to establish, well, how many of these surveys do I actually need in spite of all this variability, some of it caused by the wind farm, but how much do I actually need to survey in order to get to to be able to detect, for example, a 10% reduction? How many surveys do I need? So it's quite tedious, but I think that is actually the way to do it.
I think that was really helpful, and I think that's kind of the effort that's going on now, is how do we determine the power of the study design to actually detect changes from offshore wind developments. And it sounds like it's good that we have established some of this pre-construction information on dynamics now. One question kind of related is, if habitat models generally assume that species-environment relationships remain constant over time, is this still true with dynamic habitat models? Or I think clarifying that, is there a way to incorporate things like different life stages of a species based on the data that you have?
I'm not sure I got the last part of the question. Can you repeat that, please?
The person is asking if there's a way to incorporate information about different life stages of a species, so how behavior and habitat use might change over a species' life history.
In order to remember, the habitat models are very simple in a way. So you can predict distribution patterns and flight heights and other sort of responses, but you're not able to incorporate life stages. You're not able to mix different behaviors in one model. Only an agent-based model can do that. So that's why agent-based modeling is a necessary step on top of the habitat model if you want to include that kind of information. But that is certainly possible. We have done that for fishes, for example, we have included life stages in agent-based modeling.
And actually building off of that and agent-based models, have you been able to incorporate factors like stress response or energetics into those models to predict kind of short-term behavior and movements based on interactions with a stressor?
Yes. So we have developed, for example, a sea dog model for eider ducks, which has input data on food supply. So all the energetics are solved. We know what the stressors will be, both in terms of removal of the mussels due to the infrastructure. It's not wind farms in this case, but it doesn't matter. And then there are some indirect effect on the birds in terms of displacement. And then the agent-based model can actually be used to look at the overall impact on energetics and calculate mortality of all the individuals. And that's the best way, I think, to estimate the overall impact of an infrastructure project on any predator. But it requires lots of calibration data. For example, if we're looking at these species here, there would be no chance to get the input data on the prey species, for example, that would be required. So that's why when we talk about energetics here in the ABM models for these species, those energetics are actually proxies taken from the habitat model. So we imagine that the distribution of the animals reflects the distribution of the prey, but it may not necessarily be so. But that's simply because we don't have access to or knowledge about exactly what is the key prey for these predators in the NYSERDA area. So this could also be a priority for NYSERDA to identify those key prey species in order to be able to make much better predictions about impacts.
Well, luckily we've got another project that is looking at those predator-prey dynamics in the same area. So hopefully more on that soon. Going back to the hydrodynamic modeling, can you talk a little bit more about what kind of validation data is used for the hydrodynamic models in modeling results based on the observations? And the question is asking to particularly look at the summer months when the New York Bight coastal and shelf waters are often highly stratified and could have a significant impact on habitat suitability.
Yes, you're absolutely right, and it is worth a little bit of a headache. But we did get good calibration data. It's mainly buoy data, three-dimensional buoy data. So you have to make sure that the certification layer or the depth of the certification is predicted correctly at any one time. And you need, of course, those calibration data from several locations, both in the deep water on the shelf and in close inshore. I think we always would like to have more calibration data, but in general, I think our hydrodynamic model ended up being showing or describing certification realistically. We had an issue with what is called the cold water of Long Island. We had a problem to actually describe that correctly in the beginning, but eventually we solved it.
Thanks. We have kind of a big picture question about the ways in which climate change is impacting our planning for offshore wind development. And I think maybe bringing it back to modeling, is there a way that you can kind of incorporate that forward-thinking changes to oceanographic characteristics, or even how we can start detangling the impacts from climate change and changing hydrodynamic factors from the impacts that we may see from offshore wind development?
Yeah, I think it needs a dedicated effort where you look at the way that those things that will probably not change with the climate changes. So like the currents, for example, they will not change that much. The temperature will change a lot. So you can try to look into the influence of other factors than temperature, and then see how much how much difference it will then make if we use the predicted long-term changes in temperature and add those to predictions. But it will be, yeah, it will be very theoretical, but that's the only thing you can do. You can use some of the climate change predictions for temperature, maybe also other oceanographic variables, and include those and or to sort of project what the trends that we have now, if temperature has an influence. That is what we can do. Yeah. But it's a big, I've been involved in one project in the Baltic Sea where we made predictions up to 2,300. And that has also been published, also all the way through the ecosystem to birds. But of course, a lot of unknowns, but very interesting. So if anybody are interested, I could share that those publications.
Great, thank you. And I wonder if you could talk a little bit about the lessons learned from completing this project in the US and how you might build on the products that have come out of it, but also how you might kind of tackle this kind of problem differently in the future.
I think the most useful is that we have tried to compare using those very fine scale oceanographic data as drivers of the habitat models with data that are available just on the internet, like satellite images, for example, like bathymetry data. So those differences in the predictive power of the models using different quality habitat drivers. I think that is very interesting. So that will be part of the report to nyserda. So for some species, it is actually possible to get quite far with data that are readily available. But for other species, it actually is required to use these fine-scale oceanographic data. So I think we need to understand better what makes, in which situations do we need to have those fine-scale data available.
And I think that you talked a little bit about the report on this information and maybe where people can find the products in the future, or I know that they're not out yet, but where we might be able to find them when this project is complete.
Yes, I can share the location as soon as it is published. I'm not aware exactly where it will be published, but I think we can share that pretty soon. So it's planned to be published at the end of the year.
Excellent, thank you. And I think we might be able to wrap up a little bit early. I don't see any more questions in the Q&A, but if someone has one, another one, please submit that, and I will check again before we completely wrap up. But then maybe Sal, if you want to bring up our last slides. So everyone, thank you again for joining us for this Learning from the Experts webinar. Just a reminder that the webinar recording and presentation slides will be available at nyserda.ny.gov /OSW-webinar-series shortly after. And please check back soon on the Offshore Wind events page, wind.ny.gov, for future webinars in the Learning from the Experts series. A few upcoming topics are previewed on the slide, including offshore wind and hydrogen, national historic preservation, and offshore wind data collection and management. So a nice tie into this presentation. And if you have requests for future topics you would like to hear about in this series, please email us at offshorewind@nyserda.ny.gov or fill out our Learning from the Experts survey posted on our website. Again, thank you for joining us today, and we will see you next time.